All right, these notes are over factoring the difference of perfect squares. What is a perfect square? Well, obviously, a square in geometry is just a quadrilateral shape that has all four sides that are the same. That's kind of a simplified version. But in math, in algebra class, when we say a perfect square, we're talking about a number that is found by taking another number and multiplying it by itself. So, what does one squared mean? It means 1 times 1. Well, 1 times 1 is just 1. The number 1 is a perfect square. 2 squared just means 2 times 2, which gives us 4. 4 is a perfect square. 3 squared is 3 times 3, which gives us 9. 9 is a perfect square. 4 times 4, that gives us 16. 16 is a perfect square. 5 squared is just 5 times 5. That gives us 25. 5 is a perfect square. 6 squared is 6 times 6. That gives us 36. So 36 is a perfect square. 49 is a perfect square. 64 is a perfect square. 81 is a perfect square. 100, 121, and 144. Those are all perfect squares. All right, every single one of them. And of course, we could keep on going forever. Not going to. These are really handy to memorize, but if you get to a gigantic number and you want to know if it is a perfect square, you can just use your calculator. If you were to take the number 150 and you take the square root of a 150, you end up getting a decimal. Okay, this ends up giving you 12 point something, something, something. That's how you know this 150 is not a perfect square. All right, that's one thing I wanted to show you guys. Something else very quickly. Watch this when I multiply. Let's do 2x plus 3 times 2x minus 3. When we multiply these two values together, in our class, we used the box method, right? We created this neat little box to multiply our values. We go across the top, we go across the side. Oops, that should be a minus. My bad. Let me fix that. And we create this box. We have two columns and we have two rows. And don't forget to fill all of those blanks. You just multiply the two numbers, the one that goes up and the one that is left. All right, so 2x times 2x gives us 4x squared. In this box right here, we just go up and all the way to the left. So 3 times 2x gives us 6x. And I'm going to go ahead and put a plus 6x inside there. This box down here, we do 2x times negative 3, which gives us a negative 6x. And then our last box, we multiply 3 times negative 3, which gives us negative 9. And if you remember, our next step is to look at all of these values that we have now, and we're going to combine our like terms. We have a plus 6x and we have a minus 6x. Because those both have an x to the first power, they are like terms. And when I combine those together, 6x minus 6x, they cancel each other out to 0. So all that we have left is 4x squared minus 9. We don't have a trinomial answer. Our answer is only a binomial. And if you'll notice, this center value, this is always has to be a minus sign. And 4 and 9, both of those coefficients or those numbers, those constants are perfect squares. They were on our perfect square chart. And of course, x squared is a perfect square chart. So see if you can, or excuse me, x squared is a perfect square. See if you can notice the pattern. 2 times 2 gives us 4. X times x gives us x squared. And 3 times 3 gives us 9. As long as these two binomials have the exact same values, but this middle sign is opposite, we end up with the difference of two perfect squares. So knowing that pattern, we can always just work in reverse. Okay? So here it is written as a formula. A squared minus b squared gives us a plus b times a minus b. Of course, don't forget, you always, always, always have to look for a GCF first. You are not allowed to skip that step. All right, let's look at example 1. It says 9p to the 7th power minus 36p to the 5th power. And you guys know we always have to look for a GCF first. Both of these factors, or both of these terms, are divisible by 9. And I can also factor out a p to the 5th power. They both have a p as a variable, and the 5th power is our lowest exponent. So that's what we can factor out of both of those, 9p to the 5th power. What's left over when you divide that out? You're left with a p squared minus 4. So when I look inside my parentheses, I say, oh, well, p squared is definitely a perfect square, and 4 is also a perfect square. So I just set up my two empty set of parentheses. What value times itself makes p squared? That's p times p. And what value times itself makes 4? 2 and 2. And then we just have to make sure that the signs we use are 1 plus and 1 minus. It doesn't matter which order you put them in. You're always going to get the same answer. I just am a creature of habit, so I'll always put plus first. And we cannot forget to bring down our 9p to the 5th power. That was our GCF that we factored from the beginning. So basically, we took this entire pizza right here, our original problem, and we sliced it up into as many pieces as possible. That's basically what we just did. So if you look at example 2, 81x to the 4th minus 16. If I look at both of those terms and do some investigating, I recognize that there is no GCF. So I'm going to go straight into factoring because 81 and 16 are both perfect squares. So what value times itself makes 81? That's a 9 times 9. What value times itself makes 16? 4 times 4. But you guys might be like, Miss Gidry, we have an x to the 4th power. That's not x squared. Oh, hold your horses, you silly gooses. X to the 4th power is the same thing as saying x times x times x times x. We want to break these up into two distinct groups, but equal groups. So I can break them up so that I have two x values that we're multiplying together in each group. The first one is an x squared, and the second one is an x squared. X times x gives us, x squared times x squared gives us x to the 4th power. And of course, we have 1 plus and 1 minus, and we're done. All right, let's try another one because this is just getting used to factoring the same pattern over and over again. When I look at these values, I see that 25x to the 4th and y squared have nothing in common. They have no GCF, but everything is a perfect square. So I'm going to go ahead and set up my parentheses. 25 is the same thing as saying 5 times 5. And again, we already did our x to the 4th power, but we'll do it again just to be sure that we understand. X to the 4th just means x times x times x times x. And I see that I have a group of x's here and a group of x's here. That's an equal set. So x squared times x squared. And then we have our y squared there at the back. Y squared is the same thing as saying y times y. Well, each group only gets a single y value. So this is just y here and y here. One is plus, one is minus. Now let's look at our last one. 4x to the 8th minus 49x squared. I look at 4 and 49, our coefficients, and they are not divisible by the same value. But both of these terms have an x squared in them. They both have an x value. We are going to factor out an x squared. We always use our smallest exponent. So when I take out an x squared, we're left with 4x to the 6th power minus 49. And now I have the difference of two perfect squares. You've got to make sure it's always the difference. You're never allowed to factor the sum of two perfect squares. It's not possible. So I'm going to set up my two empty sets of parentheses. What value times itself makes 4? That's just a 2 times 2. And if we have x to the 6th power, you don't always have to write this step out, but I'm just doing it for the purpose of our notes so we always see what is happening. X to the 6th power just means x times x times x times x times x times x. So if I want to split that into two equal groups, I have an x cubed times an x cubed. So those go here and here. And then what value times itself makes 49? That's a 7 times a 7. One is plus, one is minus. And we're almost done. Oops, y'all were going to let me forget to bring down my x squared, my GCF. Now we're finished and we've factored it completely.